been a few months. I hope you enjoyed the new intro. I made the music myself in Ableton, and I made the animation in Blender. And I also redid my office, and I captured many, many pictures of my office and created a 3D model using Meshroom. So that was a fun little project. And what I'm doing here is marking a new chapter in my YouTube channel, actually. Because, well, initially the YouTube channel wasn't really meant to be, as widespread as it's become. It was actually just a response to the pandemic. I was making videos for college classes that I was teaching for my students to watch asynchronously. But I've been really so happy what happened after I decided to make the leap to make some of them public. That the community's really engaged with the videos and really enjoyed them. And it's been so nice to have that kind of engagement and impact. And so I want to keep going. There's so many things that I've learned over the years that don't fit cleanly into a course. And so now I want to go beyond the courses that I was teaching and start to talk about all sorts of cool stuff across computer science, applied math, and engineering. And so my goal is to make some longer form videos doing really deep dives into different topics. And so I have a whole laundry list of things I'm going to try. But I figured out, what better place to start than one of my favorite topics back when I was a PhD student that figured enormously into my dissertation. And that's the topic of distance matrices. And so just to show you, here's a figure from my dissertation where I show some distance matrices. So this is the first topic I'll be diving into. And what a distance matrix is basically an image or a square matrix that describes shape. And I'll go into more detail about what that means. But yeah, so just in terms of a general outline for what we're doing, I will specifically define what I mean by shape and what I mean by a distance image. I will talk about how to compute it efficiently using NumPy. Then I'll talk about some fun applications, some applications in video analysis, some applications in music analysis, and then there's like tons more applications. I'll just scratch the surface of some of them. So I'm going to do a really deep dive, and hopefully this will be nice and informative. All right, so what am I talking about specifically? Well, I told you that these distance matrices are used to describe shape. So first I should talk a little bit about what I mean by shape. And so we're going to be working with point clouds. So a point cloud is just a collection of points. But what is a point? Okay, I need to be a little bit more specific about what that means. Let me specialize myself to a Euclidean point cloud for a moment. So they call it a Euclidean point cloud. So a Euclidean point cloud is a matrix where each row is a set of coordinates for a point in Euclidean space. Okay, so Euclidean space is what we're used to. This is where we put Cartesian axis, for example, in 2 dimensions. I'll work with those mostly, but I will allude to some other examples of point clouds later. But let me start with this. So for a simple example, let me start by making a circle. And so let me say the circle maybe has 30 points in it. Let me space those equally from 0 to 2 pi. And I'm going to do this thing here where I know that actually 2 pi is the same as 0. So I'm going to do a lens space starting on 0 and ending on 2 pi. That would actually be the same point. So I'm going to choose n plus 1 points, but only take the first n. That will make sure I have equally spaced points that are all unique. All right, so I'm going to call my point cloud x here. I'm going to use that as the convention for most of what I do. And so let me go ahead and make this point cloud according to this definition that I have right here. So actually, let me call this t's, and I'll say for t and t's. I'll say x.append. All right, well, I'll make this a unit circle. And so each row is going to be a set of x, y coordinates, where the x coordinate is the cosine, and the y coordinate is the sine. And that's it. Okay, now let me make this an array object in NumPy so I can plot it easily. So I know that the first column is going to be the x coordinate, and the second column is going to be the y coordinate in this example. So here is a 2-dimensional Euclidean point cloud. And I want to put some colors on this because this is going to help me when I explain the distance image. So in order to do that, I have to say that each point is a different index here, and then I'll choose a color map. I like to use spectral in this application. It gives a nice broad range of colors that are all very unique. All right, and when I go to plot this, let me make sure I'm not tricking us with any scaling that the plot does. Okay, good. So there's my circle. Looks like a circle. Just to show you, to make this a little more exciting, I can actually, instead of doing cosine of t sine of t, if I do sine of 2t, this will turn into a figure 8. So that's a slightly more exciting curve. It's an example of something called a Lissajous curve. Let me take maybe, actually 50 is probably a good number. Okay, yeah. So this is an example of something called a Lissajous curve. Just to show you another example, I could do different coefficients in front of the sine and the cosine argument. 2, 3 gives me a little ribbon. Let's do maybe 3, 7. I got something a little crazy here. Yeah, okay, so these are Lissajous curves, but let me back to the figure 8 because this is just interesting enough, but not too complicated for me to use as an example here. Okay, just one more thing I want to point out, since hopefully we're getting comfortable now with what a Euclidean point cloud is, how each point is a set of coordinates in a different row. If I know that up front, well, there's definitely a more efficient way I can make this here than use this loop, which is just to use some NumPy broadcasting and slice-wise assignment. So I could just make this array up front. Okay, I know it has to have n rows because it's in different points, and I'm in 2 dimensions, so I know it has to have 2 columns. I can knock out the entire first dimension, the first coordinate, in one fell swoop here. I can say cosine of t's. That's going to do element-wise cosine and do this slice assignment. And then I can knock out all the sines in one as well. And this is going to be exactly the same, but just to show you, this is actually much more efficient. Okay, fine, 3 lines versus 4, but it's a lot more efficient in code. It doesn't have to do this expanding list and all these Python loops. Okay, good. All right, so there's a figure 8. Now I can define what a distance matrix is. So I'll start with the Euclidean distance matrix. Or actually, I can do the same thing. I'll give a general definition, and then I will specify that definition to Euclidean. So okay, so a distance matrix, or a point cloud with n points, is a n by n matrix. I'll call it D, where dij is the distance between the ith point and the jth point in the point cloud. And then specifically for Euclidean distance matrix, a Euclidean distance matrix has the form, so I can write this down as an equation here. So dij is equal to, okay, so now I have to actually define a specific distance, and it's based on the Pythagorean theorem. You've probably seen something like this before. In 2 dimensions, if I wanted to measure the distance between 2 points, I could create a right triangle between them, and I would have to measure the x. So the base of that right triangle is going to be aligned with the x-axis. So I could measure the difference in the x coordinates there to get that length, and then the y would be the difference. The height of the triangle would be along the y-axis there. Right, so create a right triangle, and then the Pythagorean theorem says, okay, difference in x squared plus difference in y squared is equal to the hypotenuse squared, and the hypotenuse is the length of the distance that I'm looking for between these 2 points, the straight line distance. Okay, so the straight line distance is the hypotenuse between these 2 points when I construct a right triangle that's axis aligned. And you can generalize this to higher dimensions. It's the same formula. So it amounts to just taking the square root of the sum over all the dimensions. So I'll index them maybe by k. Each dimension is going to be indexed by k up to d minus 1. So I'll say, okay, Euclidean distance matrix for a Euclidean point cloud in d dimensions has this form. Okay, so what I do is I say, okay, xi So the first point, I look at what is its kth coordinate. I subtract the kth coordinate from the second point. Then I square them. All right, so that's the Pythagorean theorem. You square them. But this is just establishing what's the length along that axis of this higher dimensional triangle that I'm constructing. So I take that, I square it, I sum it up, and then I take the square root of all that. Now, a lot of people don't like equations, but they do feel a little more comfortable in code. And this is fairly easy to write in code. So assume that I have a variable x that holds this Euclidean point cloud. I can just look and say, okay, the number of rows is the number of points I have. The dimension, the number of different coordinates I have, is the number of columns. So now I can set up this matrix here. I know it's supposed to have n by n elements because I need to compare every point to every other point. And so just go ahead and loop through. So for I in range n, for j in range n. Xi is going to be the ith row of x. Xj is going to be the jth row of x. And then to compute, I have to compute now this formula here. So I have to come up with some little variable. I guess I'll call it dij equals 0. So let me now loop through range. Okay, so I'll loop through each dimension, compute the difference, and sum it up. So I'll say dij plus equals the square difference of xi at this coordinate and xj at this coordinate. And then finally, at the end, I can assign this to my big matrix. Dij is equal to square root of dij. Okay, good. Let's make sure that runs. Okay, that runs. And let me now show that as an image. Okay, because these are matrices, but really they're images, and it's very helpful to look at them as images because you can see some patterns. So let's do that. I want to use, I like this color map for showing distances. And I want to make sure that I don't get tricked by any blurring that happens. Okay, cool. So here is the distance image for that figure 8. And actually, it's probably helpful. Oh, and sorry, I said distance image. I meant distance matrix. I'll probably mix those up a lot. But we're really talking about a distance matrix here, but we just have decided to look at it as an image. So let me put this right next to the figure 8. And, okay, so let me put the figure 8 on the left. And let me put the distance image on the right. Sorry, the distance matrix. Let me throw a color map on there so we can see these colors actually correspond to floating point values that are describing the distances. Okay. All right, so there it is. Let me also do something here to help. I said I was going to use these colors. Let me throw these colors along the x-axis and the y-axis. Give me a second to do that. Okay, here we go. So what I've done here is I've annotated each row and each column of this distance matrix with the color of the point that it corresponds to in the point cloud. So I can see this red point is actually the first row and the first column of this distance matrix. And so each pixel in this distance matrix describes one of the distances between a pair of points in this point cloud. And it actually fully describes the shape up to a rotation and translation. So if I were to, or a flip, any what's called an isometry. So I could flip this around, I could rotate it, I could translate it. That wouldn't change the distances between these points. And so this image would look exactly the same. And so if I look at the different pixels here, I say, okay, look, this pixel here is about the brightest. This is about the furthest any 2 points can be. So that's the distance between this point here, which looks to be maybe the 5th point. It's like maybe that point there. And then the other one is this like kind of brighter, kind of mid-orange point. So probably that one down there. So that's like the furthest distance it's telling me. That makes sense. I can see a similar value happens over here between this kind of yellow-greenish point, which is probably that one. And between this, so look at the row there, it's a yellow greenish point, and then the column is this like bluish point. That would be that point down there. So okay, cool. So I can kind of see that straight up. That's the diameter of the point cloud here, which is the a pair of points that achieves the biggest distance, or it's the distance of the pair of points that achieves the biggest distance. So actually 2 pairs here achieve that distance, it appears. I can also see places where the distances are very small. So between this point here and this point, so distance between I being, here's I and here's J. So distance between this point and this point is pretty small, even though those points are not next to each other as I go around the figure 8. So it should make sense that, okay, first of all, this diagonal, just as a sanity check, this is a property of a metric space. The distance from any point to itself is 0. So I see 0 along the whole diagonal. So if I equals J, then all these coordinates are going to be exactly equal, and I'll just get 0. But I think particularly interesting is some of these off-diagonal points that are close. So this is telling me, okay, yeah, this is definitely not the same point. I does not equal J, but I find that they are close by them. Let's talk about some other structures that we can find in these images that tell us about the shape. So if I go back up here and I go through actually a couple periods instead of just one time around the figure out, let me go twice around, maybe with twice as many points. Okay, and actually let me offset this just a little bit. If I make this, yeah, an odd number. Okay, so that's getting towards what I want. Now, this looks pretty interesting. I go around the figure 8 twice. I can see towards the beginning, I go around once, and then I actually go around again. And that's why it looks like those colors are interleaved there. So if I compute the distance matrix of this, I see something very interesting. I actually see an entire diagonal that is not the main diagonal. And that diagonal starts, in this case, halfway through. So if I go around, I see, okay, once around, I get to the yellow. And then the yellow is the beginning of the second time around. The second time around, I'm actually doing something very similar to what I did the first time around. And so every point on the second cycle through this figure 8 has a point close to it that occurred in the first cycle. And they repeat in sequence. So you see this point 50 is close to point 0, and then 51 would be close to point 1, 52 would be close to point 2, etc., etc. So these diagonals tell us that we have something periodic that repeats itself in sequence. Just to really drive that point home, let me go up and go through more than 2 cycles. Let me go through maybe like 4 cycles. So maybe I'll change this to 4, 1 here. Okay, so I'm going through 4 cycles here. And now I can see I actually have 3 off-diagonal repetitions. Okay. Another thing I can do is say, okay, well, at the end of this, let me put on, maybe this is just the first X here. But maybe I have just a totally different shape. Maybe just some random noise. Actually, you know what? I can, let's see, what can I do here? I will actually just change maybe the last 100 points. I'll make them just random noise offset by like 3 or something. So, okay. So I go through, in this case, 3 cycles, and then the last points are just a bunch of random points. So what does that look like? Okay, now I see this block structure. I have a bunch of points that are relatively close to each other in this block up here. And then suddenly I jump to something else in a different part of the space that's actually far from where we were at the beginning. So the block structures indicate transitions. So diagonals indicate repetitions, block structures indicate transitions. Okay, and there's just one more thing I want to show you. Let me go back, this is kind of ugly actually. Let me go back to, let me just go back to the single figure 8 for a moment. And I'll put in just a few more points just to fill it out a little more. And And okay, so let me get that original image here. I'll save it so I can contrast it with something else. So what I'm going to do here is actually warp the points that I'm taking a little bit. So I'm going to put that 2 pi on the outside to make something easy for myself. Okay, so watch this. If I take the square of this on the inside here, what that's going to do is spend a little more time at the beginning than at the end of this. And if I go and I look at the distance matrix again, I see that it's warped, but it looks the same, basically. I can see similar structures, but it's warped. So here's the original, and here's what it looks like after it's warped. So this is actually something I studied in my dissertation, is what structures are preserved and how you could match them between different versions of the same shape, but that were warped. All right, now I want to talk about some computational aspects here, because this way of going directly from the definition is kind of a horrible way to actually code it up in practice. The first thing I could do is, I don't need this inner loop. I could use NumPy operations for that. So I could certainly replace this inner loop with something a lot simpler by saying something like dij is equal to the square root of the sum of the square differences between xi and xj over all the dimensions. So now I'm taking advantage here of NumPy element-wise subtraction, element-wise squaring, summing, and square root. So that should give the same thing. Let me just check. Yep, that's all good. But actually, I can get away without having to write these Python nested loops as well, with a slightly less obvious technique. So let me go back to the definition of the Euclidean distance. And let me work this a little bit. So if the square root's a bit annoying, so let me take the square of both sides and have a look at this. And what I can do is actually FOIL this. So just do the distributive property and expand this a little bit. And what I end up getting is going to be xi at this dimension squared plus xj at this dimension squared minus 2 times xi at this dimension, xj at this dimension. Okay, so it just, going back to some basic algebraic ideas, that is how I would expand that. And what I can do is actually split the sum up into 3 pieces. And then I'll be able to do something really nice. So here's what this is going to look like. Okay, so now I have 3 pieces. Okay, so if I look at the first piece here, and if I fix I, so I'm looking at just a particular row of this. So for each element of the row, what I've got is a term that I sum on, which is the sum of the squares of all the dimensions of the ith point. So it's, for this 2D example, to be the x coordinate of the ith point squared plus the y coordinate of the ith point squared. And that's otherwise known as the squared magnitude. And you notice, regardless of what column I'm in, I'm going to add that squared magnitude to an element in that row. All right, so if I'm in the ith row, I have to add on the squared magnitude of the ith point to every column in that row. Likewise, if I'm in the jth column, I add on the squared magnitude of the jth point to every row in that column. So actually, let me start to do that in code. I can knock out these first 2 terms pretty easily by saying, all right, let me call this x sqr for the squared magnitude. So I'll say that is going to be the sum of x. So each dimension squared element-wise, and I'm going to sum over all the dimensions. So here I'll say dim equals 1. That is going to sum over all k. So over all columns, I'm going to sum up, here I am. I'm going to sum up the square of the element. And I'm going to say here, keep dims equals true. And so what this is going to do is, this is going to give me a column vector, or a column matrix. Whoops, I meant to say axis, sorry, I need to torch, I guess, right now. Okay, so yeah, this is going to give me a column matrix. And then actually, if I were to say this, if I were to say dsqr is equal to x sqr plus x sqr dot t, Okay, that's going to turn this into a row matrix of 1 by 100. And this plus here, this does something really cool. This does broadcasting. So it's going to take a column and add it to a row. And so what it'll do is the first element of that column, I'm going to add that to every element in the row. That's my first row. Then I'm going to take the second element in that column, add it to every element in the row. That's my second row, and so on and so forth. And this is very fast in NumPy. So this is actually getting me 2/3 of the way there. If I look at the shape of this, I'm already up to 100 by 100. Okay, so I've got the first two terms. That actually did exactly what I said. So the first row has the square magnitude of the first point added to every single element. The second row has the square magnitude of the second point added to every single element, and then likewise for the columns. Okay, so then I just need this last term here, which I can get with a matrix multiplication. So if I look at this, I see, well, this is actually just the dot product between the ith point and the jth point. Well, matrix multiplication is a bunch of dot products. In fact, it has every single dot product that I need here. So you could look at this and convince yourself that that would be the matrix multiplication just of x times x transpose. Right? And that gives me the distance squared. Now let's have a look at that. All right, so that's already looking pretty close. And notice, compared to this, I didn't have to have any nested loops or anything because the loops are actually happening behind the scenes in NumPy. Now, of course, though, this is the squared magnitude, so that's why it looks a little bit different. It's kind of emphasize some of the higher things, right? Because the square will make those go up. If I want to go back to the original, what I need to do is take the square root. But I think it's going to yell at me here. Let's see. Does it yell at me? Yes, it does. Invalid value encountered in square root. And what I see here is a few points along the diagonal are white, and actually turns out, let's see, I think they should be NAND. So let me see that. MP is NAND D. Yeah, okay, so they're NAND. What happened is, okay, I'm doing this in kind of an interesting way. These three pieces are computed separately, and because of rounding, I can actually end up getting something a little bit less than 0 when I subtract this off here. Mathematically, it shouldn't be, but this is because of how we compute things with floating point. And so I just need to be a little careful. Before I take the square root, let me just make sure that anything that's less than 0 gets clamped at 0. And actually, if you're doing something in Torch, and you need the distance like this, probably a better thing to do would be to make it, maybe anything less than a tiny number, make it that tiny number, just so, because the derivative of the square root function is proportional to 1 over the square root, and 1 over 0 is really bad. Okay, so that's undefined. We don't even want to get, we want to try not to get too close to that. So anyway, that's another thing you can do. You won't really notice. Okay, yeah. So going back and plotting this now, I see this looks, pretty much exactly like the first one. Okay, great. So this is my fast way of computing this, and so what I'll do is I'll just encapsulate this in a method real quick. Sometimes I call them self-similarity matrices. That's actually a slightly different idea. Let me call it just matrix. So I'll have this encapsulated here, and maybe that's a parameter I can set. So then it doesn't warn me about that. Okay. So just to check it, I'll say D is equal to get just match X. Boom, there we go. All right, so let's move beyond the figure 8 and start to talk about some more interesting applications. So the first thing I want to talk about is applications of video. So I actually took a couple videos here. Let me show you one of them. This is me putting my arm in a circle. Okay, so I'm doing something kind of like the figure 8 where, it's not a figure 8, it's a circle, but this video repeats itself, okay? And I could think of each frame of the video like a point, actually, but in very high dimensional space. So let me show you what I mean by loading this video in. I've installed the Python OpenCV library, which should just be pip open install python-opencv. And I import that as CV2, and this is going to allow me to load videos in as frames. So if I say here, okay, here's how I'm going to do it. I'm just going to loop through and load each frame. I'll say cv2.video capture circle, capital C circle dot web. Okay, so that'll get me started there. And now what I have to do is capture a bunch of frames in a loop. So this is a little weird, but I'll show you what I mean. So I'm going to say here while ret and cap dot, let's see, is opened. Okay. What I'm going to do is I'm going to say ret frame equals cap dot read. Okay. So ret is going to return true if this actually was a frame left, or false otherwise. So I'll say if ret frames dot append frame. Okay. So that should load in each frame of the video. Now what is actually here? Let me go ahead and just make this an actual bona-fide NumPy array, and I'll show you the shape of it. Okay, so this is actually a 4-dimensional array. The first dimension is the time dimension. So this is, so far following the convention that I had in my point clouds, where the first dimension is just indexing different frames. Now each frame is a point, but each frame is actually a 3-dimensional array. Really kind of like a 2.5-dimensional array, because it has rows, so each frame is an image. It has rows, columns, and it has red, green, and blue. That's the 3rd dimension there. And so actually, yeah, I'll just pull one of them out and have a look. Actually, I think I'm going to look like a Smurf, because I think OpenCV uses BGR instead of RGB. Let me see. So if I look at frame 0, yeah, okay. Do I look like a Smurf? Yeah, a little bit. Okay, but that's not important. The important thing is that the data is there. So, but yeah, if what I do is actually flatten these 3 dimensions into excuse me, a single dimension, then I can go back and I'll have this data in the format of a point cloud. So if I say frames equals mp.reshape frames, I'll keep the rows as they are, the first dimension, but I'm actually going to take the last 3 dimensions and condense them and flatten them into 1. Okay, so now I see I have the second dimension. This is quite a bit larger than the 2 dimensions that we've been looking at. So what happened is each pixel, each color channel turns into its own coordinate, its own dimension. And overall pixels, overall color channels actually have over 6 million different dimensions. But I could still do the same thing. Actually, it might be a little too slow if I try to do it on this whole thing. Let me see. I'll try it real quick. But I'll say d equal to get dismat frames. Okay, so what I ended up doing actually was rescaling each frame to be 10 times smaller across each axis, which actually means 100 times fewer pixels. So many fewer pixels are involved now. And each pixel takes up a 10 by 10 region, so it's able to actually average out some of the imperfections in my motion from one cycle to the next. So that's nice. And then when I compute the distance matrix, I get a very interesting pattern. I see these diagonals that are indicating repetitions. And so that's exactly what I talked about. And nice, so somehow actually this whole distance matrix is picking up on my repetitions of going around in a circle. And so the way that happened is I thought of each frame as a point. And then I was able to use the Euclidean similarity between frames. And so each pixel location and each color channel at the location becomes its own coordinate. And I compute the difference of that coordinate, square it, and then sum up all the differences. So it's kind of like laying 2 different images, one at one particular frame and one at another frame, on top of each other, and comparing the differences of every single pixel across every single color channel. That's what the Euclidean distance is doing here. And so that was actually able to pick up on these repetitions. And so there was a paper, a very cool paper that came out back in 2000 that used this kind of idea to analyze motions, periodic motions in videos. And what they did was when they would see these kind of diagonals indicating that they had a sequence that repeated itself, they would actually extract the diagonals and then do some periodicity analysis to try to figure out, okay, well, what is the period of the repetition here? So let's try to replicate what they did. So I have, okay, this frames here. That's my point cloud. And so I have as many points or frames. Each frame is a point. It's a little weird. It's a very high dimensional space. In this case, almost 21,000 dimensional space. So each frame is a point, and I'm going to let me extract. So there's going to be that many diagonals here that I can look at. And if I average the values along the central diagonal, it should be 0. Then it should go up, but when I get to repetition, they should average to a lower value again. Now, I see these diagonals aren't perfect. That's probably because I didn't actually perfectly go at the same exact rate around the circle, but still I see they're pretty good. But we see some of that warping that I was showing too. So we see both the diagonals, but also a little bit of the warping. But I still think that this should work. If I try to average down the diagonals and then plot that, we should see low, high, low, high, low, high, low, right? So let's see. If I do that, and let me loop through here. So I say for I in range n, diags in index I is equal to np.mean. So let me take the mean value of each diagonal. So I'll say here, this should be, I called it d, right? Yeah. So np.diag di. So this is the 0th diagonal will be the main diagonal. Diagonal index 1 will be the one right on top of that, and so on and so forth. Okay, so if I do that, then I get this very nice periodic signal. And it looks like every 40 frames or so, it has this dip, and that's what we're seeing. Okay, but if I want to estimate that precisely, I can use the Fourier transform to do it. So let me do that. That's what they did in the paper. Actually, they computed the power spectral density. So they say spectral power there, okay. So let's do it. So I'll say PSD is equal to np.fft.rfft. Dags. Okay, so I'm just doing the Fourier transform. It's going to tell me how powerful is a particular frequency over all the frequencies that go through an integer number of cycles over this interval from 0 to, I don't know, I think the video was about 10 seconds, almost 300 frames. Okay. Yeah, what is n actually? I forget. Okay, 267, so not quite 300 frames. Okay, so we got the power spectral density. Oh, actually, one more thing. Okay, I just realized we're going to see something a little weird here. My dog just wanted to go for a walk. Okay, so we'll take care of that too. But first, let me take care of. Actually, Theo, do you want to say hi? Theo, come here. Theo's going to say hi real quick. Hey, Theo. Whoops, do we see Theo? Hey, this is Theo. Theo, say hi to everybody. You're going to help us with the power spectral density? What did Daddy forget to do? I forgot to subtract the mean off of this, right, Theo? That's why we see the 0 bin is so high here, the DC coefficient of Fourier. Okay, whatever. If you've seen that before or not. Right, Theo? Okay. So, let me subtract off the mean so we can actually see the contrast a little bit better. So if I say diags, or maybe I could just do the Fourier transform of diags minus np.mean diags. Okay. Okay, so there's the Fourier transform. But let me get the units right here. So this is units of frames. This is actually units of cycles per interval. So this interval is like 270 frames roughly. That's my n here. So let me just do a little bit of dimension analysis real quick to get this right. So I'll say, okay, we start off with k cycles per interval. But I want to convert that into, first let me do cycles per sample. So I'll say, okay, there's n samples over every, or I'll say one interval over every n samples. And then let me actually convert this to cycles per second, hertz. So this video is at a frame rate of 30 frames per second. So then I'll say, okay, what I have here is actually 30 samples or frames over every second. All right, good. So let me get my units here. So this is going to be k, that's usually used for frequency index. np.a range, psd.size. And then in the numerator here we have 30. and the denominator we have n. So this should give me cycles per second. All right, so let me put the x label there. All right, so I'm seeing a peak of at around, okay, this is probably an erroneous peak. I'm not sure what's causing that exactly, maybe a little bit of the noise down here. But actually the peak that I'm seeing here is probably the right one. In fact, let me convert this, so that's frequency. Let me convert this to period. That would be 1 over frequency. So samples per second, if we're going to go, or this is in units of cycles per second, and we're going to convert this to seconds per cycle by doing 1 over this. So it's going to be, yeah, okay. So yeah, this is now samples, or this is now in units of period. So this is period in seconds. Okay. Anyway, so I see a peak of around 1.5 seconds. And that should be the right period here. So if I zoom in a little bit on that, so I'll just go from 0 to 3 maybe. Okay, so I see that peak at like 1.4 seconds. So do we believe that if I count and I watch this video? Whoop, 1 Mississippi, 2 Mississippi. Yeah, okay, I could believe that. All right, anyway, so that gives you a flavor of it. I do, though, want to point out something else that they show in the paper, which is kind of interesting. So that's for a video where, like, basically things are going around in a circle. They had an example with a dog running. So every frame of the cycle is different. But there's something else that happens when you have motions that more like walking, or like a pendulum going back and forth. So they show that here. For a pendulum going back and forth, actually, so for the first half of the period is exactly like the second half of the period, but with a mirror image of that. So what you still see these diagonals, but you also see these anti-diagonals going the other way, because as I complete the second half of my period, so pendulum goes to the right. As the pendulum's coming back to the left, I actually do the same thing I just did, but in reverse. That's why you got these diagonals going the other way. And so you see this almost looks a little more like a checkerboard pattern than just the straight diagonals. So I took another video where I kind of made that happen. So let me show you that video real quick. That video is called, let me see. It's called wave. Okay, you're right. Right. So the idea is that if I wave, then somehow that should be a little bit more like a pendulum moving, because as I wave in one direction, okay, yeah, this is a weird wave. I would say don't come any closer, all right? But as I make the X and I unmake the X, unmaking the X is doing the same thing but in reverse. So let me I'll run the same kind of code and I'll show you the result and what that looks like. And there we go. Here we see this beautiful pattern with the anti-diagonal there, exactly as I promised. All right, let me show you another application of distance matrices now, this time with music. So if I load in our favorite new intro on this channel, let's just make sure we got it. Okay, so you should have heard that a moment ago. You know it. Now I'm going to sweep some stuff under the rug here. I'm going to compute something called MFCC features. And let me actually define my hop link here. This is one step beyond. I talked about this in another video. I'll link it. But this is one step beyond something called the Mel spectrogram. But it's a way to summarize audio, getting rid of some of the noise and honing in on more of the timbre of what's going on. So what I'll do here is I'll say, okay, I'll say m is equal to librosa.feature.mfcc. Yeah, okay, there we go. SR hop length equals hop. Okay, I need to quickly look at the documentation here. Let's see. So if I put a question mark there, oops, it's okay. Y is equal to, okay, they call it Y. So they call the audio Y here. And I can choose how many coefficients I want. That's how many different dimensions there are going to be. So I can say N MFCC. 13 is a pretty common choice. Librosa defaults to 20, but I'll use 13. It's one of those magic numbers. Okay, good. Okay, so I got MFCC. Let me just show you what this looks like. Actually, it comes in transposed from how I've been doing it so far. Really, there are 750 points in 13 dimensions. So I'll have to transpose in a second, but let me just show you what it looks like. Okay, so already I can see some repetitions, kind of, because if you remember my intro codes, there's 5 chords. And so we're seeing, and the chords are each split into 8 subdivisions. So it's so 1 2 3 4 2 2 3 4 2 2 3 4 2 2 3 4. Okay, so we're kind of seeing that there, even just in the coefficients. But I should summarize these with a similarity matrix so you can really see that. So yeah, let me go ahead and do that. I'll say, okay, but I know that this is actually supposed to be transposed. So I'll say D is equal to get distance matrix M, dot.M, share.D. Okay, and so I see some of these diagonals here. Oh, and I forgot to say, I did throw some stuff at the end of this, if we listen to it, because I wanted to show a block as well. So my intro is only 10 seconds long. After it's over, and that was my YouTube intro that I just made. Yay! Okay, so I have some different stuff, and so you see like a block here. That's a different section. But then you see these diagonals here. Actually, diagonals are a little bit faint. Maybe let me hone on the first 8 seconds here. So I'll say from 0 to the sample rate times 8. Okay, now the diagonals are really clear. There's actually something else I can do if I want. That's a little trick. I could do something called a diagonal embedding, or yeah, there's some really fancy theory behind this. I won't get into it, but I'll just say librosa feature memory stack memory. There we go. So librosa feature stack memory. What this is going to do is essentially average down diagonals. So, okay, I'll say n steps equals, maybe I'll say 10 here. So I'll say n steps equals 10. Okay, now you notice the diagonals pop out a little more. Those diagonals are a bit clearer. And yeah, I bet you if I do, I'll see this even more. And if I want to try to convert the units here, I'm not going to go through the whole thing. I just went through with the video, but I'm just going to eyeball it. I'll say, yeah, this is like about 100, a repetition every 100 hops. Okay, so hop is 512 samples. So 5, 1, 2, 0 over the sample rate. Okay, so every 0.23 seconds, I get a repetition. So that must be, let's see, is this right? I said hop length equals that. 100. Oh, no, whoops. 100 times it. Okay. Yeah, 51200. Yeah, okay. So every 2.3 seconds. So that's. Yep, okay, that sounds right. Yep, I see a repetition. Okay. So there's an audio example. I definitely glossed over some of the details, but hopefully you can see that that's useful. Actually, I should point out also there is a paper that came out. There's a famous paper in music information retrieval that uses this idea to find where you go to different sections in the music, like from verse to chorus or something. You would expect to have these blocks, like I was talking about. And so this paper looks for these corners, where you have something that's all similar to itself, and then it jumps to something else that's all similar to itself, but dissimilar to what just came before it. You'll get this checkerboard pattern. You'll get these corners here. And so you basically just look for those corners. What you do is you convolve a little checkerboard pattern down the diagonal. And that checkerboard pattern will peak every time it goes to a new section. And that's how you can identify the boundaries between sections. And this ends up being the foundation of a lot of work in music information retrieval that tries to find sections. Okay. So that was cool. All right, yeah, so I did music, I did video. Just wanted to briefly talk about some other applications that I'm not going to do here, but I'll just mention. So you can even do this sort of thing with 3D shapes. You have to come up with a way of turning a 3D shape into a point. This particular paper does it using some classical embeddings, which maybe I'll talk about in another video, although they're a little bit outdated at this point. People probably want to use neural networks these days, but there's some pretty cool ways of turning a shape into a point. Something called shape distribution, something else called spin image, shape histogram. These are cool ideas. Actually, I have a notebook where I outlined a bunch of these. I'll try to link to the notebook. But yeah, so basically, you can turn an entire 3D shape into a point, and then you can look at a 3D video of somebody walking now, and you can see these same kind of patterns that we were talking about a moment ago, with that kind of checkerboard thing. Another paper is this one I really like. So they actually not just looking for repetitions, but actually trying to classify entire emotions, looking a little more detailed in these self-similarity images. And the idea here is, okay, look, if I capture a video of somebody doing a golf swing from one point of view, and I capture a video of somebody doing a golf swing from another point of view, the self-similarity matrices for those two videos should look pretty similar. Even if they're from different points of view and the geometry is a little bit different, they have the overall patterns. So it can actually identify emotion just by looking at this image. That's very cool. So I didn't have to capture it from the perfect point of view. I could actually capture it from a different point of view and get the same kind of pattern. So they talk about that. And they do show some of the same kind of examples with walking and things like that. But what I thought was cool about this paper is they were able to do a lot more. They're actually able to tell apart different actions in motion capture data and even in ordinary video. And I actually built off of this idea. Maybe I should toot my own horn for a second. I'll go to my papers here. I did actually, let's see, where is it? Yeah, I use this idea in music too, where I said, oh, actually, you know what? If you're trying to do cover song identification and you hone in on just a little chunk of audio, even if it's being played by different instruments, you can still see like the same sort of patterns. All right? So I basically followed up on their idea. That was my first author paper as a grad student over 10 years ago. Okay, and I should also mention that there is more recent work. You know, if we're talking about the modern era with deep neural networks and everything, and generative AI. Stable Audio recently wrote a paper where they actually enforced some structural constraints when they were generating longer musical tunes. So they're kind of saying, hey, I know that I'm supposed to see like these structures that Foot was pointing out, or Foot was pointing out in this paper a long time ago. So we're going to say, hey, that's what we actually, if we're generating full songs, we should make sure that we have some of the common structures that we see in real music. And so they actually incorporate that into some loss in their machine learning pipeline to generate this music. Okay, so there's tons of papers that use self-similarity matrices, but those are a few. I'll link to them in the description. Oh, actually, there is one major one I forgot. So if you go to this website, recurrenceplot.tk, there's a whole website devoted to this other one. You can use, if you turn these into binary matrices where you only you have a 1 for maybe just the nearest neighbors. So for each row you identify maybe the 10 smallest distances, and those are 1 and everything else is a 0, or vice versa. Then you create these things called recurrence plots. See, they have this nice little thing there showing you go from a distance matrix to a recurrence plot, and then you can compute statistics of these recurrence plots and can tell you things about chaos. And so people in dynamical systems are really gung ho about this, and they look at these as well. And I would highly encourage you to go to recurrence-plot.tk and check this out. You can see what they do. And actually, I used some of these features in a different paper on video analysis, where I was analyzing what are called stereotypical motor motions in people with autism spectrum disorder. These are repetitive motions that people do. And so I actually have also used these myself and found them to be pretty interesting. So anyway, yeah, that's a bunch of applications. And so there's more that I have to say about distance matrices. I'm going to make a follow-up video where I talk about something called classic multidimensional scaling. So I'm going to talk about how to go the other way. If you're given a distance matrix, how do you go back to a point cloud? But I think this is enough for now. We're at almost an hour, so I should probably stop here. I hope you enjoyed it, and I'm looking forward to making more videos for you very soon.